In this video, we're going to look at our third ideal topology, which is our series-series connection. And this corresponds to a transconductance amplifier. And so as we can see in this top circuit here, we have a voltage as our input and a current as our output. So we have input voltage VI and output current I0. And so because of that, we see we have a series connection on our input between our gain amplifier, our AG, and our feedback component beta Z. We also have a series connection on our output side. So we've sort of combined our input part of our voltage amplifier and the output part of our current amplifier. So because of that, we're not going to need to do as much analysis as we had done previously. So just like before though, we can sort of detail, we can make this more detailed by sort of breaking this amplifier up into something that looks like this. So we can say this is an amplifier which has input resistance Ri, output resistance R0, and then we see that gain block AG times the error voltage, and where our error voltage is defined over here on the left. Similarly, we can define our feedback loop in a little more detail. So this beta Z, we can represent as just a dependent source on the left, which is beta Z times I0. Notice again, we're saying that our input resistance is 0 for this feedback loop. So we're assuming an ideal feedback loop. The other thing to point out here is just like when we looked at our current amplifier, we've short-circuited this output, which basically means this R0 wouldn't have any effect when we're doing our analysis to find our gain. So there is some analysis in the notes for how to find a transfer function. It is very similar to what we saw for our other two configurations, so for that reason I'm not going to go through it in detail here, but I encourage you to look in the notes if you're interested, or of course in the textbook. So what we find is we find that our AGF is equal to AG divided by 1 plus beta Z times AG. And so this is equal to our output current divided by our input voltage. So because we have this current divided by voltage, that's why we call this a transconductance amplifier. And so this AGF would actually be our closed loop current to voltage transfer function. So current to voltage, because we're taking the ratio of the current to the voltage, and this is our transfer function. And so note once again, we have a slightly different beta variable from what we've seen in our previous cases. So here we have a beta Z, which is just our resistance feedback transfer function. So resistance feedback transfer function, and so we can see why that needs to be slightly different, because if we focus on our feedback network up here, we see we're multiplying the output current by this beta Z in order to produce a feedback voltage. Okay, so for our input and output resistances, we don't actually need to do analysis again because we've already analyzed our series input when we looked at the voltage amplifier, and we've already looked at our series output when we did the current amplifier. So nothing is going to change in that regard. So we can actually just go ahead and say our input resistance for this amplifier with feedback is given by the equation RIF is equal to the input resistance of the open loop amplifier times 1 plus beta Z times AG. Similarly, we don't need to do the analysis for our output resistance. We've already done that when we looked at our current amplifier. And so what we'll see is that this output resistance with feedback is equal to the output resistance of our open loop amplifier times this 1 plus beta Z times AG. So in this case, we notice that both of these are increasing. And so just like with every other thing we've looked at so far, all of our other configuration, this is actually going to be desirable. And in order to see that more clearly, we can look at our equivalent circuit. So here's our equivalent circuit. So let's label this as our equivalent circuit. And so just like before, we can sort of highlight an area that represents our amplifier. So we have this input resistance to our network with feedback, our transfer function multiplied by that input, and then our output resistance of the network with feedback as well. So on the input side, we see we have an RIF that is relatively large compared to the input resistance of our open loop amplifier. And so that's desirable because that means that this VI is going to be mostly dropped across RIF. So our input to the amplifier is as close as we can get to the input to the system. So we're not wasting anything on this RS here. So now if we look at our output, we see we have a current divider. So this R naught F is also large. So sort of qualitatively again, we can say our current is taking the path of least resistance. So the larger this is, the better in terms of making sure most of this current goes through our load resistor. And like we talked about with our current amplifier, another way to say that is this output current is not going to be as dependent on the value of our load resistor, which is of course a desirable property.